We're going to talk about mathematical induction today. Now, to talk about mathematical induction, we need to first talk about sets. Specifically, we need to talk about sets having or not having a least or minimum or smallest element. Right? So we've seen examples of sets that have a minimum element and examples of sets that don't have a minimum element. Some examples of sets that do have a minimum element: the natural numbers, the counting numbers, 1, 2, 3, 4, 5, and so on, they have a minimum element of 1. A closed interval of the real numbers has a minimum element. So the closed interval from 0 to 1 has a minimum element of 0. Some examples of sets that don't have a minimum element. Well, open intervals within the real numbers do not have a minimum element. So the open interval from 0 to 1 does not have a minimum element. Likewise, if I define a set to be fractions 1 over natural numbers for all the natural numbers, now every time the natural number increases in the denominator, the 1 over that number, that fraction, gets smaller, and so that set actually has no least element since the natural numbers go on forever to infinity. So let's say we have a set that has a least element. We've got some set in the real numbers, has a least element. If it does, then it actually has a unique minimum element. So let's take a look at a quick proof of that. So for the sake of contradiction, we're going to assume the contrary. We're going to say M1 and M2 are actually both least elements of A. Well, then M1 is less than or equal to M2 by the definition of being a minimum element. And M2 is less than or equal to M1 by the definition of a minimum element. And since they're both less than or equal to each other, the only option that works is that they are in fact equal to each other, which contradicts there being two least elements. So there actually is a specific, unique least element. All right. So why we care about this least element idea? We care about sets being well ordered. So we say a set is well ordered if every non-empty subset of it has a minimum element or a least element. So any finite set of real numbers is going to be well ordered. I have an example there, S. That's the set of the numbers 2, 3, 6, and 10. It's well ordered. Any set that looks like that, where I can put commas between all of the entries and I can list them all out, will be well ordered. However, intervals of the real numbers, whether they're closed or open, are not well ordered. The closed interval 0, 1 is not well ordered because the open interval 0, 1 is a subset of it that's not empty, and it has no least element. Now, it may seem simple enough that the natural numbers, the counting numbers, that 1, 2, 3, 4, 5, and so on, right, is a well-ordered set. But it turns out that we can't really prove it. So when we can't prove something, but it seems apparent to us, then we sometimes accept something as an axiom. I told you a while ago that axioms are very few and far between. This is one of the axioms that we'll take, the well-ordering principle. It says that the set of all the positive integers, or the natural numbers, is well ordered. Now, a consequence of this is that for each positive integer n, we can have some statement p of n, and if we can show that P1 is true, and the implication P of k, or if P of k, then P of k plus 1 is true for every positive or integer, then we have that P of n is true for every positive integer. So here's a proof of that. We assume to the contrary the theorems are false. So we have these conditions 1 and 2 are satisfied, but there's some integer n such that P of n is a false statement. Now, we're going to take a set. That is the set of natural numbers for which P of n is false. Well, we assumed that there is at least one integer that this is the case for, so we know S is non-empty. So it's a non-empty set of the positive subset of the positive integers. And by the well-ordering principle, we have that S has some least element S. So let's take that element S. Now, we are assuming our first and second assumptions there. So we've got P of 1 is true. So we know 1's not in S. So S is greater than or equal to 2. And we know that S is the least element, the smallest element, the minimum element in S, which means that S minus 1 is a positive integer still, since S is greater than or equal to 2. And we know that S minus 1 is not in my set S. So P of S minus 1 must be a true statement. Well, condition 2 that we assumed says P of S is true if P of S minus 1 is true. So that means that S can't be in my set S either. And this contradicts the assumption that there was some element S in S to begin with. So that means that this works. What we've just proven is actually called the principle of mathematical induction. And the consequence of this is if we want to prove a statement for all n in the natural numbers, all the positive integers, P of n is true, we can prove it by showing that P of 1 is true, and then showing the implication if P of k, then P of k plus 1 is true for every positive integer k. So whenever we complete a proof of the statement P of n this way, we're completing a induction proof or a proof by induction. That step where we show that P of 1 is true is called the base step or basis step. Occasionally the anchor, but primarily the base or basis step. It's the foundation for the whole proof. And then finally, this implication, if P of k, then P of k plus 1 for some arbitrary integer k. The statement, the part that's with the ifs, is the P of k part, and we call that the inductive or induction hypothesis. So it's very common that we use a direct proof to show the implication P of k implies P of k plus 1, but it doesn't have to be a direct proof. You can use any proof technique that we've used so far. So we have lots of options available to us. The step of showing that the implication P of k implies P of k plus 1 is true is called the inductive step in a proof by induction. So we have a basis step, we have an inductive hypothesis that we will then use to show an implication, and when we're using that to show the implication, we are completing the inductive step. So let's take a look at an example. Namely, we're going to look at the sum of the integers 1 to n equals n times the quantity n plus 1 divided by 2. So there's a result. We're saying that this is true for every positive integer n. So the first thing we need to do is prove the basis step. So our basis step says P of 1. So we plug 1 in for n, which means the left-hand side becomes just 1, and the right-hand side becomes the quantity 1 times the quantity 1 plus 1 divided by 2. So we have 1 times 2 divided by 2, or just 1. So we have the statement 1 equals 1, which is true. So P of 1 is in fact true. then we're going to assume that P of k is true. Well, assuming P of k is true, we're plugging k in for n now. So we'll have the sum of the integers 1 to k equals k times the quantity k plus 1 divided by 2. And we're going to be able to use that equation to prove that P of k plus 1 is in fact true. So P of k plus 1 says that we have the sum of the integers 1 to k plus 1 is going to equal the quantity k plus 1 times the quantity k plus 2 divided by 2. So to prove the P of k plus 1, I can't use both sides of my equal sign to start off with. I need to choose one because I'm trying to show this equality. So I need to start on one side, I'll use my inductive hypothesis, and I'll arrive at the other side of the equal sign. Now, when we're doing proofs by induction, it is always wise to start on the side that has a sum like this, if some kind of sum like this exists. So let's take a look at doing that. That sum, 1 all the way up to k plus 1, adding those integers together, well, the integer right before k plus 1 is k. So that's really the sum of the integers 1 to k plus the integer k plus 1. But using my inductive hypothesis, I know that the sum of the integers from 1 to k is really k times the quantity k plus 1 divided by 2. So I can substitute that quantity in for the sum of the integers 1 to k, and then I still have the integer k plus 1 that I'll be adding. Now, getting a common denominator of 2 between those two fractions gives me k times the quantity k plus 1 plus 2 times the quantity k plus 1 in my numerator, with 2 as my common denominator. And then I can notice that I can factor out the quantity k plus 1, leaving me k plus 1 times the quantity k plus 2 divided by 2, which is in fact exactly what I was trying to show. So, by the principle of mathematical induction, P of n is true for every positive integer n. Let's take a look at another example of this. So I have, for every positive integer n, I want to show 1 over 2 times 3 plus 1 over 3 times 4 plus all the way up to 1 over the quantity n plus 1 times the quantity n plus 2 is equal to n times, or n divided by 2n plus 4. Now, we can see the pattern happening in our denominator, and when they write it out this way, it helps us see that pattern happening. So to do a proof by induction, the first thing that we have to do is show that this holds when n equals 1. So I'm going to substitute n equals 1 in, and I will get, on my left-hand side, 1 over 2 times 3. 1 over the quantity 1 plus 1 times the quantity 1 plus 2. 1 over 2 times 3, which is 1 over 6. Now, on the right-hand side, plugging 1 in, I find that I have 1 over 2 times 1, so 1 over 2 plus 4, or 1 over 6. Since both sides equal 1/6, then the formula holds for n equals 1. So my induction hypothesis is that this holds for k. So plugging k in for n, I find myself with the equation 1 over the quantity 2 times 3, added up all the way up to 1 over the quantity k plus 1 times k plus 2 is going to equal k over 2k plus 4. Now remember, this is what I get to assume in order to prove that this is true for k plus 1. So substituting k plus 1 in, I can see that what I'm trying to show is that the sum from 1 over 2 times 3 to 1 over k plus 2 times k plus 3 equals, and simplifying out the right-hand side when I've plugged in k plus 1, gives me that I'm showing that it tries to equal, I'm trying to show that it equals k plus 1 over the quantity 2k plus 6. So let's take a look. Again, we look at the sum side to start, all right? And we're trying to get to this part by using the induction hypothesis to help us get there. So that's our proof strategy. So we have the sum that was on the left-hand side, and we note that the term right before this last one that was written is actually 1 over the quantity k plus 1 times the quantity k plus 2. Well, now this sum that's in these brackets here looks like the induction hypothesis sum. So I have the induction hypothesis sum plus that last term, 1 over k plus 2 times k plus 3. Using the induction hypothesis, I can put in place of that first long sum k over the quantity 2k plus 4. So I have that plus the last term. Now, I can notice that 2 times k plus 4 is equal to 2 times the quantity k plus 2. And that's helpful because finding a common denominator, I notice that they both already have a k plus 2 in the denominator. So I simply need to get a k plus 3 into the denominator of the first term and a 2 into the denominator of the second term. When I do that, I get in my numerator k times the quantity k plus 3 from my first fraction and a plus 2 from the second fraction. And my common denominator becomes 2 times the quantity k plus 2 times the quantity k plus 3. Now, simplifying my numerator, I find that I have k squared plus 3k plus 2. And then I notice that I can actually factor that out, and I can get k plus 1 times k plus 2 all over my denominator of 2 times the quantity k plus 2 times the quantity k plus 3. Both my numerator and denominator have a term of k plus 2 in them, which cancel out, and I'm left with k plus 1 over 2 times the quantity k plus 3. Now, distributing the 2, I get the quantity k plus 1 divided by the quantity 2k plus 6. And that is the desired result. So, by mathematical induction, I have that P of n is true for all n.